Now our last video ended with the example that we have present on the screen using L'Hopital's rule to compute the limit, this time as our variable is approaching infinity, of t cubed plus 2t squared plus 3t plus 1 divided by e to the t. Just as we did last time, we need to show that the limit we're looking at is actually an indeterminate form before applying L'Hopital's rule. However, both the polynomial and the exponential, as t is approaching infinity, both of those things are approaching infinity. So we're getting a large number over large number indeterminate form. We may therefore apply L'Hopital's rule to conclude that the limit that we are given is equal to this other limit, which is equal to the derivative of the numerator divided by the derivative of the denominator as t is approaching infinity. However, unlike our last example, when we now evaluate the limit of the numerator here and the limit of the denominator here, we don't just have a resolved situation where we get a number. Now, when we take the limit as t is approaching infinity of this polynomial and this exponential, we are still getting a large number over a large number, which is an indeterminate form. So while it's true that these two limits have the same value, replacing this limit with this limit does not immediately help us. And the question is, so what do we do? Well, we have patience. L'Hopital's rule was a good trick. It was a good thing to try, and it is a trick that applies when we have an indeterminate form. Right now, our limit is still indeterminate, but that's okay. That just means that we are still eligible to use L'Hopital's rule, and we can try using L'Hopital's rule again and see if that makes any progress. In fact, with our example, notice that by taking a derivative of the numerator, we've replaced one polynomial in the numerator with another polynomial in the numerator, but the degree of the polynomial here is smaller than the degree of the polynomial here. This tells us if we are patient and we apply L'Hopital's rule 3 times, we'll go from having a polynomial in the numerator to having a constant in the numerator. And we'll have a chain of equalities from our original limit to the limit as t is approaching infinity of 6, a constant, over e to the t. This is our terminal place because we no longer have an indeterminate form. We have a limit with a constant in the numerator and a function in the denominator that's approaching infinity. And as we've seen previously, that limit is equal to 0. So all in all, our original limit in the exercise has a value of 0. Thinking about this more generally, everything that I reasoned on the previous slide can be applied to an arbitrary polynomial divided by an arbitrary exponential function. I'm using e to the x because it has a particularly nice derivative, but I could have a crazy polynomial in the numerator and any exponential in the denominator, and we could try to use our previous example to think, how many times would I have to apply L'Hopital's rule to compute the limit as x goes to infinity of this function? Well, when I take the derivative of the exponential, it's going to remain exponential. And in fact, the derivative of e to the x is just e to the x. So no matter how many times I apply L'Hopital's rule, the denominator is going to stay the same. However, the numerator is going to keep getting, the numerator will become another polynomial, a different polynomial with smaller degree. And that can't go on forever. So after 98 applications of L'Hopital's rule, I will find that the limit of this original function right here is equal to a limit as x goes to infinity of some constant, huge constant, but divided by e to the x. And it doesn't matter how big that constant is. As x approaches infinity, e to the x will eventually get larger than that constant. So all in all, this function will have a limit of 0, and that's going to apply for any function that has a numerator, which is a polynomial, and a denominator that is exponential when we're looking at a limit as x is going off towards infinity. Taking yet another step back, when we're looking at a polynomial divided by an exponential, the limit as x is going to infinity, we believe that we're going to get 0 from L'Hopital's rule. However, this fraction is an indeterminate form of the form large number divided by large number. If we're getting a limit of 0 from that, what that must be saying is that the large number in the numerator is nothing in comparison to the large number in the denominator. The large number appearing in the denominator must be much larger than the large number in the numerator. And that tells us that eventually exponentials are much bigger and have a faster rate of growth than polynomials. And that leads us to our final topic, which is rate of growth of functions. If we have two arbitrary functions, so stepping away from the polynomial and exponential example, suppose we have two functions f and g, both of which are approaching infinity as x is approaching infinity. And we then look at the ratio of those two functions, f of x divided by g of x, and take a limit as x is going to infinity. A priori, that should be an indeterminate form of the form large number divided by large number. If, by some mechanism, we're able to determine that that indeterminate form actually resolves to infinity, or negative infinity, minus signs are okay, then what that would be telling us is that the large number in the numerator is much, much bigger than the large number in the denominator. Or in other words, that the f of x function grows faster and gets bigger than the g of x function. So that's a definition for us that will be helpful because we want to think about functions and their relative strength, which ones grow faster than the other ones, to help us glance at limits at infinity and try to figure out what we think those limits should be. So we've done one example with rate of growth between polynomials and exponentials, where we determined that exponentials grow faster than polynomials. Let's make another comparison as an exercise. Let's take a look at an algebraic function and a logarithmic function. In computing this limit, practicing an application of L'Hopital's rule, can you determine if one of these functions grows faster than the other function? I'll leave that to you as an exercise. And then more generally, what we're trying to get at is big picture. We have these four different classes of functions: trig functions, polynomials, logarithms, exponentials. Which has the slowest rate of growth and which has the fastest rate of growth? That's a question that we'll want to resolve, and we'll work together in person to figure out.